So now we're going to start seeing some where the denominator is a binomial. Filling in the empty degrees with 0x to the power, to some degree, okay, whatever the degree is. Talk more about this, but so I'll demonstrate this first part. It says fill in any empty degrees with 0 times x to whatever the degree is. So if you look at a difference of squares, right? So if you had like 4x to the power of 2 minus 9, like this, it's missing a degree, right? You have a degree 2, you have a degree 1, which isn't shown, and then you got this 0 degree term. What it's saying here is that you could, if you wanted to, you could rewrite it with that degree in there. So then you would have 4x squared plus, again, you'd show it as 0, its degree is 1. Again, this is now in descending order, and then you'd have the minus 9 right there. Now, is that important? I mean, if you're gonna do this by factor by grouping, that would work. But we don't really need to show that once we figured out we had the difference of squares, which is more like an algorithm. But now, for some of these division type problems, we may need something like this if we see that one of those terms is missing. So you got to be careful with that, okay? Now the dividend, that's the numerator, it must be in descending order. So this one was in descending order, was just missing this middle term. Well, what this is saying here is that you don't want to see lower degree terms and then higher degree terms. So you don't want to see something like x squared or 3x squared plus 4x to the power of 5 minus 8. This is out of order, descending order, right? So you'd have to say, well, I'm going to rearrange this in descending order, so it'd be 4x to the power of 5 plus, again, you could show the missing terms here, 0x to the power of 4 plus 0x to the power of 3 plus 3x squared plus 0x and then minus 8. Sorry, got kind of cluttered there at the end. But you don't necessarily need those, you know, so you could just say, well, that's descending order too. That's fine. But again, we're probably going to need some of those 0x terms if we see any that are missing. So if the divisor is a binomial, ignore the second term. Figure out how many dividends will go into the first term and multiply the binomial by that value. What we're trying to do here is to get the we're trying to see how many of something goes into something else. That's what division is. But we don't really, in the binomial, we don't care about the second term. Okay, so like a binomial we've seen before, x minus 2, right? If I'm looking to see how many of these go into x squared, I really don't care about the minus 2. I just care about the x. So the first term, that's all you're concerned about. We do work with the second term, but the first term is really all that we're trying to get, essentially to match with whatever this term is, right? So like this one, you'd say, well, how many x's go into x squared? An individual x would, okay? That doesn't have to make sense right now. We're going to see this. But this is how you do long division with these polynomials. Long division, though, right? If you saw something like 2 over 3, long division sets up as 2 divided by 3. Okay, the numerator goes into the division sign, inside, I'd say inside, and then the denominator's on the outside. Okay, so if you saw something like x over 4, again, long division would show x divided by 4, right? So these fractions, again, the denominator's on the outside with this division. How many of these go into this thing? Example will kind of clarify what we're talking about. But again, it's important to put this into long division format. So this one, let's go ahead and set this up. I'm gonna see if I can do this decently. That's not my worst, so I'm gonna keep it. So my numerator goes inside my long division symbol, 9x to the power of 3 plus 57x to the power of 2. Oh, by the way, this one's already set up in descending order for us. Thank you for that. Minus 39x plus 30. And this is being divided by x plus 7. Okay? Now, the other thing with long division is that you remember whenever you find your quotient, this is where my quotient goes. But when we find a value that goes into the quotient, remember you kind of multiply it back, but you have to multiply by both of these terms now, okay? Now, that's the only time I'm really concerned about the plus 7, okay? So again, we say, well, how many x's will go into x cubed? Well, two of those will go into x cubed, so I'm going to make this x squared, right? So, again, putting this back into the division, x squared times x, hopefully we can remember that again. X squared times x gives me then the x cubed, but we used up those x cubes, right? Now the problem here is if I subtract this, I would still be left with 8x cubes, right? Because you'd have 9x cubes minus 1x cubes, that's 8x cubes. We don't want that 8x cubed there. What we'd like to do is zero this 9x cubed out, right? So that's one way to get rid of the x cubed, but I need 9 of them. So I go back up here to the quotient. I say I'm gonna need 9 of these x squareds multiplied by the x to get rid of the 9x cubed. So now I got 9x squared times x. Now it's 9x cubed. And again, why is it subtraction? Because that's what division is. It's saying that we've used up, by multiplying these, we've used up the 9x cubed. Okay, so that does zero that out, all right? But like I said, you can't just multiply by the x. You got to multiply by both of these terms. So then I'd have to take, here I've got, from this, I don't know where to show it, I now have to take my 9x squared and multiply it by 7. Okay, now that's going to give me 63x squared. So I end up, by multiplying by 9x squared with 7, I'm ending up with an x squared term, and I can see my x squared term here. Okay, so I don't want to pair it with my x's or my constants, but I've used up, so I'm subtracting 63 of my x squareds. Okay, and that again comes from the 9x squared. I'm multiplying here. So what's left over? I'd have negative 6x squareds, but then I have everything else that I drop. Right here. It's kind of like what we would see with long division of place values. So I got minus 39x plus 30. Okay, so this 9x squared, again, that's part of my quotient. And now that I've done that, I'm not focused on this original part of the expression. Okay, I'm focused on this one now. So I go in here and I say my x's, right? Okay, so I need to make it an x squared. So that means I would have to multiply an x by an x. Okay, because x times x, that's going to give me this x squared. But see how it's not just 6x squared, it's even a negative 6x squared. So I'm going to have to, I'm going to need to be able to add here. And so it's kind of like we're taking away the negatives. That means I'm going to have to make this a minus sign. And I'm going to need 6 of them. Okay, so this is now negative 6x times x, which would be 6x squareds. But again, since it's negative, I'm now adding those in, taking away those negatives. Okay, so again, what does this do for me? It zeroes this out. But again, I now need to multiply my negative 6x by the 7, which would be a negative. So I'm going to have to add that as 42 x's. So again, we focus on the first term in the binomial, but you need to do whatever you have in your quotient. You got to multiply both terms in your binomial there, okay?
Well, what did negatives?
Another way to say this, right? So remember up here I did 9x squared times the x, and then I was subtracting for both because it was, when I multiply these I end up with positives, so I take them away. It's kind of like, well, if this number is positive, then I'm multiplying by a positive. This one was negative, so I need to make this a negative here. That's another way to look at it. So as I go through here and I'm going to continue evaluating this. So negative 39x's plus 42x's, that would be 3x's. And then my plus 30, again, that drops. So again, is this next term, is it going to be positive or negative? Well, this is a positive 3x. And so I am expecting my quotient to be, the next term of the quotient to be positive. Okay, because again, it's a positive 3x. This positive times a positive is going to make this a minus. Okay, well, I don't need to multiply by an x because this one has an x. What I then need is 3 of those x's. So I'm going to make this a 3. Again, 3 times x would be 3x that I've used, so I'm going to have to take those away. All right, and then in addition to that, right, 3 times the 7 there would be 21, but again, we've used those up. Okay, so 3x's minus 3x's, that does zero out. 30 minus 21 is 9. This is my remainder, by the way. So my final answer ends up being the quotient because, and you may be saying, well, what happened to the 30? Well, we used up 21 of the 30, but I can't really do anything with this 9 and the x. Okay, you could say, well, you could divide it by x, but we're just going to declare this the remainder. Once you can't work with the x's any longer, because there's pretty much always going to be x's in these now, you're pretty much done, okay? So on this one, we have the quotient, 9x squared minus 6x plus 3. And then we can just say that, yeah, we got the remainder of 9. On the assignment, sometimes it's 2 boxes. They'll say, what's the quotient? This is your quotient. What's the remainder? It's 9. You just fill in the 2 boxes. Sometimes, though, it may say, well, we don't want you to show the remainder as a separate box. Well, if that's the case, then you're going to have to put this in here like this. But then the remainder, right? This is what you got remaining from there. And so we take that and we add it into this. The remainder is, again, it's 9 parts out of the x plus sevenths. So it's just, that's all that remained out of whatever we were dividing by, which in this case was x plus 7. Again, is either one better than the other? I don't know. But they're going to ask for either one sometimes. Sometimes they'll ask for this one, sometimes they'll ask for this one. Both are good.
No factoring a 3 out of that?
No need. Oh,